All right, so let's have a look at how to do some acoustics in Praat, how to really like dig in and play around with some of the concepts that we've learned this week, basic sound properties. So first of all, you will want to get a hold of Praat and let's see, there we go. There's the website. I'll put the link in the description for convenience if you haven't got it. It's up in the top left corner where you can download it for Mac, for Windows, for Linux, Chromebooks. It's a somewhat involved process. Even the Raspberry Pi, if you're that nerdy. Although if you're that nerdy, you may not be needing this. Anyway, and I'm putting together a document. It's going to include some of the stuff from our live demo here. So let me just increase that a little bit so you can see it more clearly somewhat. So we'll be creating a sine wave in Praat, looking at some of its properties and doing a bit of calculations to double check stuff, and then we'll create a more interesting sound. We'll actually record some speech and do similar calculations from that, and I'll share this document as well. So what you'll want to do first is launch Praat, and if you do that, when you launch Praat, you get these two different windows, and I'm sorry that they're going to be a little bit small. The objects window and the picture window. Now, if you wanted to create illustrations for a paper or, say, a report for a course that you're taking in phonetics, the picture window is where you would assemble those illustrations, and then it can be files, sounds can, or images can be shared as various formats that you can then plug into a word processing document. We're going to ignore that for now. We're just going to be working with the objects window. So the first thing that we're going to do is we're going to create a tone, and we can do that under new sound. We're going to create a sound as a pure tone. That means pure tone is another way of saying a sine wave. And now this interface I know is really small. Essentially, we decide the name of it, how many channels, if it's going to be mono or stereo, for example. We have no reason to go for stereo right now. How long it's going to be. By default, it's 0.4 seconds. Sampling frequency, something that we learn about in a bit later in this course. The tone, so that's the actual frequency of the sine wave, and its amplitude. So right now the frequency is set at 440. We'll keep that in mind, and the amplitude is set at 0.2 pascals. Now this is kind of a pseudo pascals. What it really means is 0.2 times the maximum amplitude that can be represented digitally. Excuse me. And then there's a sort of fade in just to make it sound a bit better around the edges. So I'm going to just create that with all of the default values. And then I'm going to hit view and edit because we want to have a look at this. Now this looks a little bit messy because there's a lot of cycles. There's 440 per second and we're at 0.4 seconds. So yeah, a good 100 and some cycles here. But let's just zoom in with the zoom button in the lower right corner. And the more we zoom in, the more we see something that really does look like a sine wave that we're used to seeing. Now, what things do we want to look at? We want to look at the maximum. Now I can click over here where that sine wave hits pretty close to its peak, and it's getting pretty close to that. You see the somewhere in the middle here, this blue number on the side tells me the displacement. Right, the displacement is how far the pressure is displaced from the zero line, which is this dotted blue line here. Okay, so right here the displacement is 0.1. If I get over here, it's actually 0.2. Remember, that's what I set as the amplitude of the wave when I had it created. So that is what the peak is going to be. Other things we want to look at, we've seen the zero line, positive and negative zero crossings. You see here the line is going up and it's crossing zero, and I could try to poke around and try to find it, or I can go into the select menu and I can move the cursor to the nearest zero crossing. This is something that you often want to do in acoustic analysis, and it gets me right there. The number isn't actually zero, but it's something times 10 to the negative 7, so it's effectively zero. So that's a positive zero crossing, or I could go over here and do the same thing, and I've hit a negative zero crossing. Okay, we've talked about displacement, we've talked about amplitude. The peak-to-peak amplitude, if I go to where it seems to be maximum, 0.2, where it seems to be minimum, negative 0.2, well, the distance there is 0.4, so that would be the peak-to-peak amplitude, 0.4. Okay, normally we're not going to work with that, we're just going to work with the straight amplitude. Okay, there are some other things that we might be interested in. So if we go back to our demo thing, we might be interested in the frequency. Notice none of the things that we've looked at so far are actually frequency. Now, what is frequency related to? Well, frequency is related to the period. Now, I could try to approximate, matching the peaks, but another thing I can do is use that same select menu. I want to move the start to the nearest zero crossing and move the end to the nearest zero crossing. Now I know this is at a positive zero crossing at the start of my selection, and the end of my selection is also exactly at a zero crossing because of that menu item. And it tells me that the period is 0.002273 seconds. Okay, and in brackets, Praat automatically calculates, okay, well, with that, if this selection represents a period of some sort, which is one of the more common things you might want to do when you select something, then the frequency corresponding to that period is 440. You can manually calculate 1 divided by the period, 1 divided by this, and you will discover that it turns out to be that, 440 hertz. Notice 440 divided by seconds. So a hertz is basically an inverse second, so that's just a slightly eccentric way of representing hertz. So that works out. That's the answer that we expected. Okay, we might also be interested, remember that we've got our peak at 0.2 units. We could convert that to decibels. Oops. There we go. And we have a formula. 20. It's not entirely clear from the textbook whether you use the 20 or the 10. I'm actually going to use the 10 here just because this is going to work out well for a later illustration that I'm going to do in this video. And so if you work out mathematically, let's see, I've actually found an online calculator. Let me call it up here. Where did I put it? There we go. Oh, that. So if I want 10 times, under the functions, I have log here, and my amplitude I've identified as 0.2, and I want to tidily close that brackets. Why am I not dividing by something? Well, I've chosen to do the full scale amplitude. Full scale amplitude, if you remember from your reading, it represents the amplitude relative to the maximum that you can represent. In this case, the maximum you can represent is a value of 1. So we're taking the log of 0.2 divided by 1. Anything divided by 1, the 1 kind of disappears. It's magically unimportant. So we can just take the log of 0.2, multiply that by 10, and we get negative 6.9, about negative 7 decibels. Okay, so if you create a sine wave with an amplitude of 0.2 in Praat, you should be able to get a result that's exactly this value. If you create an amplitude that's lower than 0.2, you should have a lower amplitude, or one that's further into the negative, right? If you create a higher amplitude, it'll be more a lower magnitude, be closer to 0. And if you create a wave whose magnitude is 1, which is the maximum that can be represented digitally in Praat, then its amplitude should be 0, because its amplitude is exactly the same as the reference, the full scale reference, right? If you have a reference that isn't the maximum possible, then amplitudes above your reference are going to give positive decibel values, and the amplitudes below will give negative. Amplitudes that are exactly the same will give us 0 decibels. Okay. All right, I think that's about as much as we can dig out of a simple sine wave. They're fascinating and awesome, but let's try something even more interesting. Even more interesting. So I'm going to go back to our objects window here, and now we're going to record a mono sound. That's the first item under the new menu. And when I do that, it shows up on my other window, but I'll drag it over. We get this interface. We can select mono or stereo, various other options that we can select. I'm going to stick with the defaults now, except I'm going to say the word phonetics. So that's what I'm going to name this thing. I'm just going to hit record phonetics. Okay, and you could see the levels jumping around a bit while I said that. I'm going to click Save to List and Close, and I see that an object called phonetics, sound phonetics, has popped up in my objects window. I hit View and Edit, and you see that was what I was talking about before. And then here, this bit is phonetics. Right, that's our sound. Okay, so I'm actually going to zoom into that selection with the SEL zoom button. You notice there's a lot of sort of gunk in the background here. That's just the background noise in my recording environment. This isn't the most ideal studio recording environment, but it's going to be totally fine for what we want to do here. And I'm going to focus on the vowels for now. We can get into the acoustics of other sounds later in the course. So we have phonetics. So the f, that's the f, the fricative, and that's the s. But we kind of have 3 bulges. The phonetics. Phonetics. So let's look at the middle one. Sure. And if I hit that, if I just play that, there's not much to it. But anyway, I'm going to zoom into that. Now we have a much more interesting thing happening. I'm going to maybe zoom in a little bit more just to clear things up. So what we have here is a repeating cycle, but it's no longer a sine wave, right? It's a much more complex wave. It sort of goes short jiggle, long jiggly bit, then a short jiggly bit, then a long jiggly bit. And that kind of repeats with some modifications. You know, some of the peaks are getting higher, some are getting lower. Maybe some of the jiggles get worked out and some more are introduced. That's a highly technical way of putting it, I know. But it's still a cycle, and we can still do all the same things. I can select a point and find the displacement at that point. I can try to find a spot and move to a 0 crossing. I can hold down the Shift key and find a more or less matching spot. Move the end to a nearest 0 crossing. So now I have a full cycle of that. And there's more cycles after and more cycles before. But that's a full cycle. And that cycle goes, it takes 0.007965. Praat does kind of an arbitrary precision thing here. That's saying there's 7.965 milliseconds in that cycle. About 8 milliseconds. And in if a cycle is 8 milliseconds long, that corresponds to a frequency of about 125 hertz. Okay. I'm just writing that down for reference. I'm also interested in the peak. If I sort of back off a little bit, I'm going to reestablish that vowel and zoom there. You'll notice that whatever I'm looking at, whatever portion of the sound I'm looking at, it scales so that the highest point on that waveform is right at the top and the lowest point is right at the bottom. So I can automatically read off in this stretch of sound what the highest peak is and what the lowest trough is. Okay, so I'm going to just take the peak for no particular reason. You can either go for the peak or you can go for the maximum absolute displacement when you're looking at amplitude. Some people would take 0.05432 as the amplitude here. I'm going to take this for no particular reason. 0.04297. And Praat is going to say that's in pascals, but we know that that's a somewhat arbitrary scale. And I'm going to do something else. I'm going to zoom back out to the whole sound, and I'm going to look at that first vowel, which looks like it has a higher amplitude. Sure enough, when I look here, I look across, that's 0.08698. Okay. And I'm actually, because I can, I am going to also measure the frequency of this vowel with one of these cycles. So I'm going to zoom in a little bit more so this is easier. Select about a cycle, and then I'm going to do my move the start to the nearest zero crossing, move the end to the nearest zero crossing. So here I have, it is a slightly shorter window. The previous one was about 8 milliseconds. This is 0.007338, so it's just over 7 milliseconds. And in brackets it says that corresponds to about 136 hertz frequency. The other was 125, so this is about 11 hertz higher frequency based on this one individual cycle. Now I want to zoom out. So I've identified already that this first vowel has higher amplitude than that second vowel, and it also has higher frequency. But these amplitudes are in arbitrary Pascal values, and remember, one of the strengths of the decibel measure is that it gives us a lot of power to compare amplitudes, right? We have one value and another, and because it's done on a ratio scale, the comparison in decibels is closer to the sort of scale of comparison we get in our head than a comparison in pascals. That's because of the log scaling. So let's do that calculation. So I will call up our math here, and in this case, inside the logarithm, I'm going to take the higher value, 0.08698, divided by the lower value, 0.04297. And what this calculator is telling me is that the difference is 3.06 decibels. So I think one thing I want to remind you of, because why did I use that particular value? Why didn't I say one value divided by my, some other reference and compare it to another value divided by that reference? Well, the thing is, the decibel value, it's telling me, it's log scaling the ratio between one amplitude and another amplitude. If I had a reasonable other arbitrary reference to use, maybe the full scale reference, the one, and I took the decibel value of one of my measurements and the decibel value of the other, and I subtracted them, it would give me this value of 3.06 decibels. And that's what's really interesting and relevant to the linguistic measurement. The absolute values, the sort of raw relative to an arbitrary reference, are arbitrary, right? But comparing one vowel to another, that's no longer arbitrary because it's within the thing. If I knew what the threshold of hearing was and I had everything perfectly calibrated, I would still get this 3.06 decibel difference. So yeah, 10 times the logarithm of one of the sounds divided by the other sound. The one of the amplitude pressure amplitude measures divided by the other pressure amplitude measure. Okay, so I've got this 3.06 decibel difference. Fine. Now let me show you how most phoneticians would do it rough and ready without having to do any of that math. I think the math is important. It helps you get ahead for what's going on there. But let's see a different way to come at that. So let's go back into our sound, and we're going to, excuse me, we're going to look at some of these other menus. So first of all, let's look at pitch. This first option is show pitch. And when I do that, I get this blue line superimposed over my spectrogram. And that blue line is Praat trying to automatically track the pitch of the sounds in my recording. And isn't that handy? Remember the caveats that we have from the textbook, from what we've been learning, that it can be very hard to track pitch. And sometimes when the computer thinks it's tracking pitch, it's doing nothing of the sort. It's kind of throwing up garbage. So you need to have a sense of what pitch means and what the things in the waveform and elsewhere should look like to get a meaningful pitch. You're the backstop for the potential failings of this system. But let's see what we have. Now, when we manually measured one of those cycles, we got a period in that first vowel, or a frequency in that first vowel of 136 hertz. Now, as I move this around, you'll notice that I now have this new scale on the right side of the spectrogram in blue, and it's all measured in hertz. These are the pitch tracking. So the pitch tracking algorithm says, I'm going to assume that the pitch is between 75 and 500 hertz. So this blue thing is on that scale rather than the 0 to 5,000 hertz that the spectrogram is on. And my selection is at a point where it's guessing 135.7 hertz, which magically is really close to the 136 hertz that we calculated based on our manual measuring of the period. Okay, it's not magical. It's because ultimately we're measuring the same thing that the algorithm is measuring. And in this second vowel, we measured a frequency of 125 hertz. And when I select somewhere in the middle of this vowel, we get 124 hertz, right? And if I move around, I might get different values. So that's reassuring. It tells me, and as a phonetician, if I'm doing pitch tracking, I would be doing exactly this. I might get Praat to automatically tell me the pitch values because that's easy, but I'll spot check it and just make sure because I know that it can get bad. I did a lot of research on vocal fry at one point, and it tends to wreak havoc with pitch trackers. So I have had to do a lot of manual checking and fixing of pitch tracks. Anyway, so that's pitch. What about amplitude? I'm glad you asked. I'm going to just turn off because I don't like things getting too cluttered. I'm going to turn off the pitch tracker. Intensity. Let's show intensity. So now we have a yellow tracker with green markings at the edge that go from 50 to 100 decibels. Okay. What's that relative to? Don't worry about it because we're only going to be asking about differences. Remember that we identified a difference of 3.06 decibels between that first vowel and the second vowel. So let's look. The peak in that first vowel of this yellow thing looks like it's about 61.93. So I'm going to write that down, 61.93 decibels. And the peak, why am I asking the peak? Because that's how I calculated the decibels manually, is I looked at the peak amplitude of each of these vowels, right? So the peak here, it looks like it's about 59.34. Okay, so what's the difference there? 61.93 minus 59.34 is, hold on, I get 2.59. I did that manually on paper. 2.59 decibels. Now 2.59 decibels is not, I mean, it's a fair distance from 3.06. It's half a decibel away, right? So I mean, proportionally that's a fair distance, but half a decibel is actually pretty small. So I'm not too displeased with that either. I would point out that the intensity measure is doing something slightly different. It's doing a root mean squared business across a window rather than just getting an absolute amplitude peak like we did. So that will contribute to a slight mismatch between the amplitude that you measure manually, as I showed, and the amplitude that you get out of this automatic track. But there we have it. We have we've looked at a lot of different things. We've seen some of the similarities between what we've been looking at in sine waves, which never occur in speech. We get almost kind of somewhat close to it in some speech sounds, but not meaningfully helpful. Uh, what we can do in sine waves in terms of identifying parts of the wave, doing measurements, and what we can do in the more complex and interesting waves that we get in speech. And we've also looked at sort of manual versus automatic identification of pitch and amplitude. So I hope that's helpful. I do encourage you to play around in Praat a little bit. We're doing a whole bunch of acoustics. We have a lot more acoustics ahead of us. The more comfortable you are, sort of just poking around and having a look at these things, the more you'll be able to really consolidate the things that you learn over the rest of the acoustics stuff in your head, because you'll be able to try it out. You'll be able to make connections between what you're reading, what I'm talking about in the videos, and what you have direct experience with looking at your own speech in Praat. So I do encourage you to do that. I hope this is helpful, and yeah, I'll see you online.